Semaphore is a synchronization primitive used in concurrent programming to manage access to shared resources. It controls the number of threads that can access a particular resource at a given time. A semaphore has two main operations: wait, decrement, and signal, increment. It uses a counter to track available resources, with a count greater than 0 allowing access, and a count of 0 blocking further access. Semaphores are crucial for avoiding race conditions and ensuring proper synchronization in multi-threaded applications. A semaphore is a synchronization tool used in concurrent programming to control access to shared resources by multiple processes. It is defined as a record structure that holds two key components: value, an integer that represents the count of available resources, can be positive or negative depending on how many processes are allowed to access the resource. L, a pointer to the list of blocked processes. If a process cannot access the resource due to the semaphore's value being 0 or negative, it will be blocked and added to this list. In our implementation, we define the semaphore as C copy typedef struct int value, the semaphore value indicating resource availability, struct process asterisk L, list of blocked processes, semaphore, key operations block. This operation suspends the process that invokes it. When a process tries to access a resource, but the semaphore's value is less than or equal to 0, it is blocked. The blocked process is added to the semaphore's list of processes, L, wackup, P. This operation resumes the execution of a blocked process. It removes a process from the blocked list, L, and allows it to proceed, usually when the semaphore's value has increased, indicating that a resource is available. Summary: semaphores are crucial for controlling access to shared resources in multi-threaded or multi-process systems. The block and wackup operations provide a way to handle resource contention, ensuring that processes don't interfere with each other while using shared resources. In concurrent programming, a semaphore is a synchronization mechanism that manages access to shared resources by multiple processes. It maintains an integer value that represents the number of available resources, and a queue, L, that holds blocked processes waiting for access when resources are unavailable. The two primary semaphorations are: 1. Wait, S, action. The wait operation attempts to decrement the semaphore's value. If the value becomes negative, this means the resource is unavailable, so the process is added to the list of blocked processes, SL, and the process is suspended using the block operation. This ensures that the process will not proceed and resource becomes available. PGSQL. Copy s.value. If s.value less than 0, add this process to SL, block, to signal, S, action. The signal operation increments the semaphore's value, indicating that a process has finished using the resource, or that a resource is now available. If the value is less than or equal to 0, this means there is at least one blocked process waiting. The signal operation removes a process from the blocked list, SL, and resumes its execution with the wackup operation SCSS. Copy s.value++. If s.value less than equals 0, remove a process P from SL, wackup P. Key concepts: blocking. When a process cannot access the resource, it is added to the list of blocked processes. Waking up. When a resource becomes available, a blocked process is resumed. Semaphores are essential for ensuring mutual exclusion and preventing race conditions in multi-process environments, allowing processes to safely share resources without conflict. Deadlock occurs when two or more processes are stuck in an infinite wait, each waiting for an event that can only be triggered by one of the other waiting processes. This creates a cycle of dependency that prevents the involved processes from making any progress. Deadlock example: consider two semaphores, S and Q, each initialized to 1, indicate a single resource is available for each semaphore. Two processes, P0 and P1, are executing the following operations: P0, wait, S, P0, acquires resource S, wait, Q. P0 then tries to acquire resource Q, but Q is held by P1, so P0 waits. P, wait, Q. P1, acquires resource Q, wait, S. P1 then tries to acquire resource S, but S is held by P0, so P1 waits. At this point, both processes are waiting for the other to release a resource. P0 is waiting for P1 to release Q. P1 is waiting for P0 to release S. Consequences of deadlock: circular wait. Both processes are in a waiting state, forming a circular dependency, where P0 waits for P1, and P1 waits for P0. No progress. neither process can proceed, as they are each waiting for an event that can only be triggered by the other, leading to a deadlock. Deadlock prevention resolution. To avoid deadlock, systems must ensure that resources are allocated in a way that avoids circular dependencies. There's a mechanism to break the deadlock if it occurs, such as preempting resources or terminating one of the processes. Understanding deadlock is crucial for designing systems that handle resource allocation safely and efficiently. Starvation occurs in a system when a process is perpetually denied access to the resources it needs to proceed, even though those resources are available. Unlike deadlock, where processes are stuck waiting for each other, starvation happens when a process is continuously overlooked or preempted in favor of other processes. Cause of starvation. In semaphore systems, starvation can arise if a process keeps waiting for a resource that is repeatedly allocated to other processes. This typically happens in systems with poor scheduling or resource allocation policies, where some processes may have higher priority or are always able to acquire resources before others. Example: consider a system with two processes, P0 and P1, and a semaphore S initialized to 1. If P0 keeps acquiring the semaphore first, and P1 is unable to acquire it because of frequent interruptions or unfair scheduling, P1 may never get a chance to proceed. Consequences of starvation. Unfair resource allocation. A process may be indefinitely delayed from accessing necessary resources. Inefficiency. While some processes make progress, others are unable to proceed, leading to overall system inefficiency. Priority inversion. Starvation is often associated with unfair scheduling, where low-priority processes prevent high-priority ones from obtaining resources. Prevention of starvation. Fair scheduling. Algorithms like round-robin, or first-come first-serve, FCFS, to ensure that processes are given a fair chance to execute. Aging. Implement an aging mechanism where processes that have been waiting for too long are gradually given higher priority over time, ensuring they don't starve. Starvation is a critical issue in resource allocation systems. Mechanisms must be designed to prevent it, ensuring fair access to resources for all processes. In concurrent programming, semaphores are used to manage access to shared resources, and there are two main types: binary semaphores and counting semaphores. These types differ in how they handle synchronization and resource management. 1. Binary semaphore, also known as a mutex. A binary semaphore has only two possible values, 0 and 1. It is primarily used to implement mutual exclusion, mutex, ensuring that only one process can access a resource at a time. Value 1 indicates the resource is available. Value 0 indicates the resource is unavailable, and other processes attempting to access it will block. Binary semaphores are used. There's a need to protect a critical section of code or resource, ensuring that only one process can enter at a time. 2. Counting semaphore. A counting semaphore can hold any non-negative integer value, representing the number of resources available. It is used when multiple identical resources need to be managed. Value n represents the number of available resources. Value 0 indicates no resources are available, causing processes to block until a resource becomes available. Counting semaphores are useful for managing access to pools of resources, such as a limited number of database connections or printers. Summary: binary semaphore, limited to two values, 0 and 1, used for mutual exclusion. Counting semaphore can represent a count of resources, allowing more flexible management of multiple instances of a resource. Both types of semaphores are critical for preventing race conditions and ensuring proper synchronization in multi-threaded or multi-process systems. A binary semaphore is a synchronization tool that can only take two values, 0 or 1. It is primarily used to implement mutual exclusion, mutex, to ensure that only one process can access a critical section at a time. In this implementation, we'll use two binary semaphores, S1 and S2, and an integer to manage the synchronization of two processes. Data structures. Binary semaphore S1, S2, two binary semaphores used to control access and synchronization between processes. Int c, an integer variable representing the initial state or value of the semaphore S. Initialization. S1 equals 1, initial S1 is set to 1, indicating that the first process can access the critical section. S2 equals 0, initially, S2 is set to 0, meaning the second process must wait. C equals initial value of semaphore S. This represents the number of available resources, or the initial state of the binary semaphore. Key concept: S1, binary semaphore, controls the access to the critical section. If S1 equals 1, the process can enter. If S1 equals 0, the process is blocked. S2, binary semaphore, acts as a signal to alternate processes. When a process finishes its critical section, it signals S2 to allow the other process to proceed. Workflow. Process 1, it waits on S1, blocking if S1 is 0. Once it finishes, it signals S2, allowing the other process to proceed. Process 2, it waits on S2, blocking if S2 is 0. Once it finishes, it signals S1, allowing process 1 to proceed. This alternation between S1 and S2 ensures that the processes take turns accessing the critical section in a mutually exclusive manner, preventing race conditions. The use of a binary semaphore in this way effectively serializes the execution of multiple processes, ensuring safe resource access. Semaphores are widely used in concurrent programming due to their powerful synchronization capabilities. They offer several key advantages in managing access to shared resources and controlling process execution. 1. Prevention of race conditions. Semaphores help prevent race conditions by ensuring that multiple processes or threads do not simultaneously access critical sections of code or shared resources. By controlling access through semaphore operations like wait and signal, semaphores enforce orderly resource allocation. 2. Simple synchronization. Semaphores provide a simple, low-level mechanism for synchronizing multiple processes. They ensure that processes either wait for resources to be available or are allowed to continue execution when resources are free, making them effective for resource management in multi-threaded environments. 3. Efficient resource management. Semaphores, especially counting semaphores, allow for efficient management of multiple instances of a resource. They track the number of available resources, make it possible to allocate resources without oversubscription, and ensuring fairness in resource distribution. 4. Deadlock avoidance. When implemented carefully, semaphores can help avoid deadlock situations. By using proper locking mechanisms and acquiring resources in a consistent order, semaphores can prevent processes from being caught in a circuit condition. 5. Flexibility. Semaphores can be applied to a variety of synchronization problems. They work for both binary, mutex, and counting semaphores, allowing for flexible control over the allocation and deallocation of resources. 6. Simple to implement. Semaphores are straightforward to implement in operating systems, application-level concurrent systems, making them a commonly used tool in process synchronization. Overall, semaphores are an effective and essential tool for synchronizing processes, preventing conflicts, and managing shared resources in multi-process and multi-threaded systems. While semaphores are useful for synchronization, they have several drawbacks. Complexity in management. Using semaphores incorrectly can lead to complex bugs, such as deadlocks, race conditions, or priority inversion, especially in large systems. Risk of deadlock. Improper ordering of semaphore operations, like acquiring semaphores in different orders, can result in deadlock, where processes are stuck waiting indefinitely. Starvation. If not managed fairly, semaphores can lead to starvation, where some processes are perpetually denied access to resources. Difficult debugging. Debugging semaphore-related issues can be challenging, as problems might only appear in specific timing scenarios.